Welcome back, everybody. We're going to finish up 1.4 today with our fun cases. These are these strange and interesting cases. And then we will we'll start up on 1.5, hopefully finishing it. If not finishing it, we'll leave the last little bit for Monday of next week and go from there. So, as we said before, one of the tricky things about square roots is that when you take the square root of a square, it's the absolute value of x, not just x. Same thing is true. You don't need to write this down, but the same thing is true with the fourth root of x to the fourth. This is equal to the absolute value of x. The sixth root of x to the sixth, absolute value of x. The 700th root of x to the 700th, equal to absolute value of x. The cubics, not so much of a problem. The odd roots, because you can plug in negative numbers into odd roots and get something that's fine, right? The third root of 8, negative 8, is negative 2. So third roots, they're fine. Fifth roots, they're fine. They can handle negative numbers just fine. It's the even roots that cause problems. Now, as another note that I realized I should write here, recall composition rule for limits is that the limit as x approaches a of f of g of x is equal to f of the limit as x approaches a of g of x, provided f is nice at the value limit as x approaches a of g of x. I'll explain that again when you write it down, but recall that you can bring the limit on the inside of a composition. So in this case, we're going to be able to bring it inside the square root, provided that the square root or the fourth root or the third root or whatever is well defined there. As long as it's okay. We have a formal definition that says that as long as f is continuous at this value, remember, limit as x approaches a of g of x is going to be a number. I mean, as long as it exists, right? But as long as g, like the limit as x approaches a of g exists, it's going to be some number. And as long as your function is like your outer function, your outer composition function is nice there, you can do this. If it's not nice there, you cannot do it. And we'll see the duality on one of the examples here in just a second. So, because of that fact, the limit as x approaches positive infinity, inside of that radical is fine because you're because you get positive infinity squared, which is going to be positive infinity. There's not going to be a problem there. So, what we're going to do is we're going to rewrite this. This is equal to the limit as x approaches positive infinity of 2x over the square root of x squared. Now take a second to understand why that's true. Convince yourself of it. Why might that be the case? Why can't I just make it the square root of x squared? Take a second to think about that. Has a big deal to do with this. We're approaching infinity, which means that plus 2 isn't going to do anything. 1 million squared plus 2 is virtually indistinguishable than 1 million squared. That plus 2 does not do anything in the face of positive infinity. Positive infinity squared plus 2 is the same thing as positive infinity squared. So we can just ignore that plus 2. We can ignore any of the smaller degree terms. And then that means that this is equal to the absolute value of x. However, I can immediately drop the absolute value now and say that this is equal to x here because what? Because it's positive infinity. Exactly right. If your values inside the square, not inside the square root, if your values inside of the absolute value are going to be positive, then the absolute value sign is redundant. It doesn't matter. just like the absolute value of 5 is just 5. We didn't do anything to it because it's already positive. So it's x here because x is approaching positive infinity. I'm going to circle this. Positive. So because we're approaching positive infinity, that absolute value sign is unnecessary and we just drop it. So this is equal to the limit as x approaches positive infinity of 2x over x. The x's cancel, and we're just going to have the limit of 2. So the final answer is 2. Because the limit of a constant is the constant itself. Any questions on that? Let's see the next one to understand why we have to be careful. So similar situation, this is going to be, it's the exact same expression, it's just now we're approaching negative infinity, which is still okay. You might be thinking, oh no, negative infinity square root, but remember that's x squared. Because so negative 1 billion squared is the same thing as positive 1 billion squared, because the negative sign cancels out because you're squaring it, right? So we're not going to have any issues on this one. So we can just write this as the limit as x approaches negative infinity of 2x over the square root of x squared. Which once again, this will be equal to the absolute value of x, but because we're approaching negative infinity, the values inside of our absolute value are negative. And so in order to take care of that, the absolute value sign tacks on an extra negative sign. So it becomes negative x here because x is approaching negative infinity. Because we're approaching negative infinity, our x values are going to be things like negative 10 billion, negative 10 trillion, negative 10 trillion to the 10 trillion. And so in order for the absolute value to make that positive, it tacks on this extra minus sign. So that's why it's going to equal that. And I'll give you another intuition behind that as well. So this will be the limit as x approaches negative infinity of 2x over negative x. The x's cancel, but we still got that negative sign there. So this is going to equal negative 2. Any questions on that? You see the stark difference? Because we were approaching positive infinity, the absolute value stayed positive on the first one. And because we were approaching negative infinity, the absolute value tacked on that extra not minus sign because our x values were going to be negative. Next problem. Unless there's any questions on this. It's okay for them to be questions. Once again, I'm going to remind you of this fact because it's okay to ask questions. I know the soul patch is scary. I know it is. It's super intimidating and awesome. I get it. It's radiating. I know. But I'm really nice. I promise. Yes.
Could you explain again why the square root was able to be converted to absolute value?
So that is a fact about the even radicals. And so I want to show that's an excellent question. Why is this true? You don't need to write this down, but why? Let's use purple. Why is this true? So the reason for that, let's just assume for the sake of an argument that it wasn't. Notice that the left-hand side is always going to be positive, right? Because it's a square root. No matter what we plug in, like regardless of what's on the inside, the square root is always a positive number. But x could be positive or it could be negative. So the problem arises when we try and plug in. So x equals 5, no problem. Because like that'll be true. The square root of 5 squared, that's equal to the square root of 25, which is equal to 5. So square root of 5 squared equals 5. Fine. But what ends up being a problem is the negative numbers. If I try and plug in -5, it won't be a solution to this expression because you'll get the square root of -5 squared. Does that equal -5? When I plug in -5 in for x, do I get a true statement? And I won't, because this will be the square root of 25, which is +5. And does +5 equal -5? No, it does not. So in order to ensure that this is a true equation, you tack on the absolute value sign, because then this is the absolute value of -5, which makes it +5. Does that make sense? Great question. That's a very, very important question about radicals. So, and that has to do, like, there is a little bit of hand waving there, specifically because they're about the concept of the principal square root. If you want to know more about that, there's a principal square root and there's a non-principal square root of things. But we always deal with the principal square root in mathematics. So, okay. Excellent question. Next one. The limit as z approaches positive infinity of the fourth root of z to the ninth plus z plus 2 over z squared minus 1. Same situation. Because z is approaching positive infinity, inside will be nice and neat. Because we're going to be plugging in a positive number to the ninth power is still a positive number. So we can technically bring what's going on. The reason why, another reason, I meant to mention, why is this going to be -2? Because the denominator will be a positive number, right? Regardless of what x is, the bottom will be a positive number, but the numerator will be a negative number. So that's why it's a negative over positive, which results in a net negative. And the reason why I'm able to drop the 2 intuitively was because it does not matter in the grand scheme of things. The positive infinity, the infinity just dominates. It eclipses that +2. But another reason is, since that will work, you can bring the limit onto the inside. You don't need to write this down, but this is just side note land, if you'd like to write it down. The limit as x approaches negative infinity of the square root of x squared plus 2, because this is going to be well defined, you can bring the limit onto the inside, right? The composition rule. This becomes the square root of the limit as x approaches negative infinity of x squared plus 2. And then remember this rule from way back when? As x goes to positive or negative infinity, a polynomial will follow the tendencies of its highest degree term. So you can just ignore everything else. So when it comes to this problem, you can just rewrite this as the square root of the limit as x approaches negative infinity of x squared. And then finally, this is the formal reason. This fact is true because it's an equality. It's true in both directions. So I can then do a kind of a circular argument and bring the limit back out front. Does that make sense? So I can rewrite this as the limit as x approaches negative infinity of the square root of x squared. That's why I can do it in formal lingo. But the intuition is sufficient for me, because that +2 will not matter as we're going to positive infinity. We'll just ignore it. Same situation here. Because we're approaching positive infinity, the +c and the +2 inside the fourth root, they do not matter. Sure, 1 billion is a big number, but 1 billion to the ninth is bigger than that by a factor of 1 billion to the eighth power. It's a lot bigger. So this is equal to the limit as z approaches positive infinity of the fourth root of z to the ninth divided by z squared. Oh no, how do I cancel? Because that's not a factor, that's not an exponent. Do you guys remember that rule about radicals? How you can convert from exponential to radical form and back and forth? Very, very useful trick, especially when we get to derivatives. But this is equal to the root goes below and the power goes above. So it's going to be z to the 9/4. So this is equal to the limit as z approaches positive infinity of z to the 9/4 divided by z squared. But remember, z squared is the same thing as z to the 8/4. So I'm going to do this little algebra over here. Z to the 9/4 over z squared is equal to z to the 9/4 minus 2, which is going to be z to the 1/4. Because you're going to get 9/4 minus 8/4, which will just leave you with 1/4 left. Any questions on that? It's okay if there are. That's the algebra going on here. So when you have same base, in this case z raised to 2 different powers, and you're dividing them, you take the difference of the numerator minus the denominator. The exponent of the numerator minus the exponent of the denominator. 1/4. So this is equal to the limit as z approaches positive infinity of z to the 1/4. And what will that be equal to? Close. Positive infinity.
Yeah, I said, is that?
Oh, did you say just infinity?
Yeah.
I thought you said negative infinity. No, you're absolutely right. Positive infinity is the correct answer. Because as z gets larger and larger, z to the 1/4 will get larger and larger. Very slow, right? See here. 10,000 to the 4th power, or the 4th root, is just 10. So it takes a long time, 10,000 x values out, and we're only at 10. But eventually, as we go to positive infinity, it will blow up forever. If you look at the graph of z to the 1/4, what it looks like is like this. And you see that it does increase slowly, but it does increase. Now this one, immediately I know the answer. What's the answer to part D? Careful. Anybody know? It does not exist. Take a second to try and figure out why. Because you need the inside to give you a positive number, but that's z to the 9th. Odd powers keep negatives negative, right? -1 to the 15th is -1. -5 billion to the 9th power will be a negative number because you've got an odd power, which means you have an odd number of negatives, which will result in a net negative. So as z approaches negative infinity, z to the 9th plus z plus 2 will also approach negative infinity. And therefore, and thus, the 4th root of z to the 9th plus z plus 2 will not exist. Because you're trying to take the 4th root of a negative number, and we can't have negatives on the inside of a we can't have negatives inside an even radical. Square root can't have a negative number. 4th root can't have a negative number on the inside. 4 billionth root, that's an even number, can't have a negative on the inside. If this had been a 3, everything would be fine. You could do this one, and you'd actually end up getting negative infinity. Yeah, you'd end up getting negative infinity. So as a fun little problem for this weekend, to hang out with your bros or your bras, you know, crack open a cold one, which I believe means Mountain Dew, right? Pretty sure that means Mountain Dew. Code Red specifically. Do they still sell Code Red? They do? Okay. But if you want to verify that the 3rd root of z to the 9th plus z plus 2 over z squared minus 1 will give you negative infinity. Good problem to try. Okay. Now we come to, legitimately, I stole this from my graduate textbook because I think it's a very, very silly problem. And I just want to show you how mathematicians think. So z goes to positive infinity. Or sorry, x goes to positive infinity. 2x will go to positive infinity as well. It'll just keep increasing. It's going to be 2 times infinity, which is still infinity, once again. And then the square root of 4x squared will also go to infinity. So you're going to get infinity minus infinity, which doesn't which is an indeterminate form. We don't know what it is because which one's going to infinity faster? Is 2x going to infinity faster, or is the square root of 4x squared going to infinity faster? What we know is that they're going at relatively the same rate because the square root of 4x squared is roughly equal to 2x, right? This right here, you don't need to write this down, but this is roughly equal to 2x because it's going to increase at roughly the same rate. I guarantee you if you plug in 10 billion, they're going to be roughly the same number. 2x and the square root of 4x squared plus 1, if you plug in 10 billion, they'll be roughly the same number. So we have to think outside the box. We need to figure out, I'm going to claim that it's probably going to be 0, but I need to verify that. I can't just claim that infinity minus infinity is 0. So someone throw out an outlandish idea. When you're faced with a problem that you have no idea how to start, just try. Just try. What's the worst thing that can happen? Right? So I see something minus a radical. Does anybody have an idea? If I see something minus a radical, when have we seen that before? You saw it, yes. Conjugate. Very, very good. Because a conjugate would get the square root. And that's going to be the problem here. The square root is the problem. So what I'm going to do is I'm going to treat this as over 1, and I'm going to multiply by the conjugate of the numerator. 2x plus the square root of 4x squared plus 1 divided by 2x plus the square root of 4x squared plus 1. Very good. Very good. This could work, could not. Who knows? That's why we have that right there, the eraser. If it doesn't work out, we're fine. It will work out, but either way. So remember, when you're multiplying by conjugates, you just square the first term and subtract the square of the second term. So this becomes 2x squared, 2x quantity squared minus the square root of 4x squared plus 1 squared, all divided by 2x plus the square root of 4x squared plus 1. And you see that we've kind of gotten rid of the issue because as x goes to infinity, if you're adding to infinities, that's just infinity. Right? That'll blow up to infinity. So this will be the limit as x approaches positive infinity of 4x squared minus 4x squared plus 1 divided by 2x plus the square root of 4x squared plus 1. And when I distribute that, I'll write one more step and then I'll claim the answer. And this will equal, once we distribute that minus sign, we'll end up with the limit as x approaches positive infinity of -1 over 2 plus the square root of 4x squared plus 1. And I'm going to claim that that's going to equal 0. And I'm right. I want you to think about why. Take a second to digest it. Why would it be 0? A second. Think about it. Okay, if you don't see it. Yes.
What happened to the x next to it?
I have no idea. I don't know why the 2 went away. the X, excuse me, 2X. Thank you for catching that. Making sure you guys were staying at attention. Even I can make a mistake. So the reason why it's 0 is that as X goes to positive infinity, this, let me highlight it instead. This right here will also approach positive. This will approach positive infinity as X goes to positive infinity, which means we're going to have -1 over infinity, quote unquote, which will go to 0, right? You take a finite number and divide it by infinity, it's going to go to 0. 1 divided by 10 billion is like 0.00000001, and that's just 10 billion. What about 10 trillion to the 10 trillion? 1 divided by 10 trillion to the 10 trillion is virtually 0. If you plug that into your calculator, guarantee you it's going to give you 0. The calculator won't, like, technically speaking, it will be a long string of zeros and then a 1, but your calculator won't be able to handle that and it'll just say 0. Okay? In stark contrast, this one right here, the limit as X approaches negative infinity. As X approaches negative infinity, this will be quote unquote negative infinity minus infinity. But if you take negative infinity and subtract off an infinity, that's going to be negative infinity. And no work needs to be shown. Is that okay? The reason why this one is negative infinity is because 2x is going to go to a negative infinity. The square root of 4x squared plus 1 is going to go to positive infinity, but you're subtracting it. So you've got negative infinity minus infinity. Those are same, like that's really the same thing as adding 2 negative infinities. Or negative infinity plus negative infinity. However you want to view it, 2 negative infinities makes a negative infinity when you add them together. Okay. Weren't those problems cool? Involving the absolute value, pretty fun. At least I think so. I love the nuance. Okay. Any questions before we get started? All right. Well, actually, let's take a small break. Let's come back at 10 o'clock. People watching, make sure you do some guided meditation or something like that. Clear your head. All right, we're back. So a couple things about the quiz I can hand it back. One quiz does not define who you are as a mathematician. It does not say that you can't do mathematics. Sometimes I've failed my fair share of quizzes and exams in mathematics. In Math 309 at UW, which was differential equations part 3. I failed my final exam and it bombed my grade heavily. And I still made it, so it's okay. It happens all the time. It will not make or break your grade. One thing I know that I've promised you, if you look at the syllabus, that I dropped 2 quiz scores. I'm not dropping them yet, and the reason for that is if it drops it now, let's say you got a 1 out of 10, your grade technically is a 10%, but it will drop it and tell you you have a 100%. So I don't drop it until there's at least about 4 quizzes on your on the grade sheet, because that gives you the most accurate representation of your grade. And I don't want you to go into an exam with a false sense of security. So, yeah, that's why I will make sure that happens a little bit later, but right now it's not going to drop until about week 7 or something like that. Once we have a lot more on our grade book, and then the dropping will be more accurate. Okay. The other thing is, please always check my grading. Please always make sure that I've added everything up correctly. I usually try to make sure that the actual score in a problem is circled. Unless you got it all correct, in which case I sometimes don't write it. But I'm human too. Every once in a while, I forget to add things. I miss a problem and I don't add it. So please let me know. And then also, if you think I graded a problem unfairly, I'm always open to hear that. What's the worst thing that can happen? You should always try to advocate for yourself. If you think you deserve more points, feel free to talk to me. I'm not infallible. So, and I don't take offense if you want to try and get more points. The worst thing that'll happen is I'll say, I'm sorry, I can't give any more points for that. That's how I decided to mark it down. But it could be a situation where like, yeah, I see that I graded that a little harshly. I can give you points back. The only time where you don't want to bring that up to me is if I gave you more points. Please do not tell me. Because then I have to give it away. I have to take points away. I'm kidding. I wouldn't. I already gave you the score. I'm not gonna go back on my word. Anyways, okay, we go to the last section of Unit 1, which is continuity. The coolest and most important topic for mathematics, completely useless in the real world. The reason why it's so important is that continuity proves is required for a lot of important theorems in mathematics. For us, most functions that we see are continuous where we need them to be. But it is in order to prove a lot of things in mathematics, continuity is required. The extreme value theorem, which we'll see in Unit 3, requires continuity. The mean value theorem in Unit 3 requires continuity. The intermediate value theorem, which we'll see at the end of this, requires continuity. All of these theorems require continuity because continuity is such a powerful tool. But in the real world, not much. So a function is said to be continuous at x equals a if the following are true. So the first thing you need is that f of a exists. If f of a does not exist, you're immediately done. The next condition is that the limit as x approaches a of f of x exists as well. And the last condition is that f of a equals the limit as x approaches a of f of x. We need all three. If any are not satisfied, then f is not continuous at x equals a. So if any of these things is broken, if f of a doesn't exist, not continuous. If the limit doesn't exist, not continuous. Even if they both even if they both exist, if they're not equal, not continuous. And I'll show you examples in the next problem to show you what breaks, like how you can see the breaks of these things. Technically speaking, this statement is all you need. That's the formal definition of continuity. However, I find that to be something that students don't recognize. You should check both of those things, because if you can check to make sure that the f of a, even if f of a and the limit exists, they're not equal, you're done. But anyways, I'm getting sidetracked. So those are the three conditions. The function has to exist at the x value, the limit has to exist at the x value, or the a value in this case, and they need to be equal there. So if a function is not continuous at x equals a, we say that it is discontinuous at x equals a. And if a function is continuous at all x values, we say it is continuous everywhere, but I don't write that. So we just say continuous. If the function is continuous everywhere, we just call it continuous. The graph of a function is continuous if it is quote unquote connected. And intuitively, what I mean by that is you can trace the whole graph without ever lifting your pencil from the page. I guess technically a pen if you want to be a real badass in mathematics. If you write with a pen, you're more powerful than me. Just because it came up in my other class, I had a student write it. Please don't write your quizzes or your exams in red pen because I grade in red pen. And so if you're great, if you write in red pen, then it's hard to see my comments versus your work. So please avoid using red pen. If you only have a red pen on you, just let me know and I will try to give you something else. Anyways, so as long as you can trace it without ever lifting your pen from the page, it's continuous. So let's look at each of these ones to see what condition is being broken. So this one right here, this function is not continuous. I don't know. Why did I write C? I need to just change that. That's an A. Sorry. Why did I do that? And I don't want to go like, I didn't I'd have to remake these graphs because I don't have them saved. And I don't want to rewrite them that time. That's going to be annoying. So this one, it's hard to see when it's zoomed out like this. Like, yeah, see why it's continuous, right? And that's not just, but if we zoom in, I'm just going to redo these ones and make that circle bigger. Desmos got a lot of upgrades since I started. You can actually make your circles larger. So anyways, the issue is that f of a doesn't exist. F of a does not exist. The limit does, right? Because as you approach it from both sides, it'll equal that y value, whatever it may be. And so intuitively, and sorry, people watching, I guess I can try and do it. If you're tracing along the curve, once you get to A, you have to lift your pen off the page and then redraw it. I know we draw a circle. I know you can technically, those are pictures, right? Where you try and draw a car without ever lifting your pen. So yeah, you can, technically speaking, right? You could go, oh, I'm just going to draw the circle and then continue onward. Yes, I know you can cheat that, but that's supposed to be a placeholder. So if you were to draw this in the real world, that open circle wouldn't be there. It would just be a hole and you would never be able to draw it. So when you're drawing with your pencil, tracing it, I have to lift my pen off the page and then continue onward. That's why it's not continuous. There's a break in the graph there. The next one here, what is the issue being broken here? The limit does not exist. The limit does not exist. Very, very good. The limit as x approaches a of f of x does not exist. Because one side of the limit is going to a number, like the left-hand limit is going to a larger number than the right-hand limit. This one here, what condition is being broken? The limit does exist, the function exists, but they're not equal. So even though f of a and the limit as x approaches a of f of x exist, we have the issue that the f of a does not equal the limit as x approaches a of f of x. That is the condition that is being broken. Condition 3. In order, so imagine if you're tracing this with your pen, you have to draw it. You have to lift your pen off the page, fill in this solid dot, then jump back. You had to lift your pen from the page. That's why it's not continuous. But even though the limit exists and the function exists, it's not enough. They need to have the same value. Limit and the function have to have the same value. And last but not least, this one here. What's the limit as x approaches a? Positive infinity. But remember, as we said in 1.4, even though we say that the limit is positive infinity, the limit does not exist. So limit as x approaches a does not exist. Yes, it equals infinity, but that still D&E. C 1.4, unit 1.4, for a more verification as to why that's true. So yes, we're saying that the limit is positive infinity. And like you could even argue also the fact that infinity doesn't equal this value. There are two options to say that the reason why this is discontinuous. One option is to say that the limit does not exist. The other option is to say that the limit and the function are not equal, because this is a finite value, whatever this may be, and infinity is a non-finite value, so you can't claim that they're equal. So either way, I'm not going to test you on this, but if you want to get really particular with the terminology, examples A and C, the two on the left, are what we call removable discontinuities. And the reason that they're called that is that all you would need to do to remove this discontinuity would be to just fill in the dot or move the dot down. So as long as you were able to just cancel this and just fill it in, you'd be good. That's why it's called a removable discontinuity. And if you want to sound really intense with your family members when you go home for spring break, you can say a singularity. You can also call it a singularity, a removable singularity. That's what they call it in complex analysis. So the study of complex calculus, which just sounds way cooler. Come on, singularity, discontinuity, singularity, way cooler. Sounds like you're talking about a black hole. Part B, example B is what we call a jump discontinuity. And there's a really, really scientific reason for that, because it jumps. It's not really scientific. It's very, very unoriginal. And then last one, part D, is what we call an infinite discontinuity, because it's going to infinity. Infinite discontinuity. You do not need to memorize these words. That's why I haven't written them in red. Usually I write things that are definitions in red. These are just if you want to be more formal with the terminology. I'm not a person who gets really, really caught up with terminology. Formal mathematical explanation, yes. But if you call it the top part, I'm not going to shame you for of a fraction. I'm not going to shame you for calling it the top part and not the numerator. And same thing here. It's a discontinuity. That's all you need to say. But if you want to be more particular. All right. Cool type of problem. This is a problem that's supposed to practice a little bit of our pre-calculus and our calculus terms. Does P of 5 equal 2? No, it is not. No. P of 5 is equal to 4. That's solid dot because you got an open circle. So the limit, as x approaches 5 of P of x is equal to 2. P of 5 is 4, but the limit is equal to 2. So that's a removable discontinuity. But either way, the limit as x approaches -4 from the left, -4 from the left, we approach 3. And yes, technically I didn't draw arrows, but Desmos doesn't have that feature yet. At least last time I checked, we can't add arrows to the end of a function. So we just have to imagine that they're there. I usually add them in on my graphs if I put them on the exams. But the limit as x approaches -infinity is going to be positive infinity. It's going to keep going up and up and up and up and never stop. So its y values are increasing indefinitely, which means the answer should be positive infinity. Next, very classic example is find all the values of X for which P is discontinuous. So we're gonna look at this. And I'm gonna write them up here so we can see it together. What values is it discontinuous at? Feel free to say them, like you don't need to do them in order. 2 is one of them.
-4.
-4 is one of them because the limit does not exist. 0 because you got an infinite limit. 2, Esrom said 2. And then what else? And then 5. Yes, 5. And so I'm going to explain why. Because so like we're going to write the reason that it's being broken. So those are the only values. So as a hint, wink, wink on the upcoming exam, it's usually a question that everyone gets to be asked on their limit exam is it continuous? Explain mathematically. So when I say justify your answer mathematically, I want a formal mathematical definition. I don't want an intuition. So if you're describing why it's discontinuous at -4, it's not because there's a jump. It's not because you have to lift your pen off the paper. Those are intuitions, but the reason for it is that the limit does not exist. So if that was a question on a quiz or an exam, hint, wink, wink. You see, I'm winking. You know, that might be something to make sure you know how to do. We all good? We would say it is discontinuous there because the limit as x approaches -4 of f of x, or p of x, excuse me, does not exist. 0. Why is 0 a discontinuity? Same thing, the limit does not exist. You could also claim that the limit is not equal to the function there. That is also sufficient, but a more apt description would be that the limit does not exist. Two, why is 2 discontinuous? Why are we discontinuous at 2? Take a second, let everyone get a chance to think about it. I'll put the picture back up here. Why is it discontinuous at 2? Does the limit exist?
Yeah.
Yes. Does the function exist? No. That's the issue. So f of 2 does not exist. And last but not least, number 5. Why are we discontinuous at 5? Well, the limit exists and the function exists. The function is equal to 4, but they're not equal. So the limit is not equal. So the limit, or f of 5, is not equal to the limit as x approaches 5. Not f, sorry, p. So that's all you need to write. You just, that would be a mathematical justification saying what property of continuity is broken. If this is like a 3-point problem, I'll give you 1 point for writing out the correct discontinuity. And if you do an intuitive justification, I might give you a half of a point extra, or maybe 1 if I'm feeling extra generous. But in order to get a full credit, you need to show a formal mathematical argument, meaning that you need to show which property is being broken. Okay. Any questions on those? You got 30 minutes? Good. All right. So how do you know if you're given the graph? It's not too terrible to figure out. All you need to look for is just where your pen lifts the page. That's what you need to do. But and I didn't show that, but that's what I do in my head is I'm drawing it. Oh, I have to lift my page. So -4 is 1. Oh, I have to lift my pen from the page. That's another one at 0. Up, I have to lift my page, like my pen from the page, 2, and then I draw again. Up, I need to lift my pen from the page, done. Pencil, rather. So that's all fine and dandy if you're given the graph, but I don't know about you. I know what this looks like roughly. I know it's a polynomial, but how do I know where it's continuous without graphing it? Like this one, hard to graph, but you might be able to do it. This one, maybe be able to graph it. This one becomes a lot harder. So how do we know it? Theorem 1.5.1. Polynomials are continuous everywhere, and all rational functions, root functions, trigonometric functions, basically every function we've ever experienced, whether it be in pre-calculus like exponential and logarithmic and root functions and rational functions, or in trigonometry with trig and inverse trig, they're all continuous on their domains. Piecewise functions have their own problems, but every other function that we've encountered, they're just continuous on their domains. And do you remember how to find domains? You look where the function is undefined. So main issues, making sure you're not dividing by 0, making sure that you are not taking the square root of a negative number. And then last but not least is making sure that you're not taking the logarithm of a negative number or 0. So this first one, it's polynomial. Polynomials are nice. They're one of the best functions out there. They're continuous everywhere. So continuous everywhere. Because polynomial. Polynomials are one of the nicest functions we know what to deal with. Polynomials are awesome. Part B. G of x is equal to 3x squared minus x minus 2 over x squared minus 1. Let's see this. Notice that 1 is a factor of the numerator and the denominator. Right? So don't write this down. I want you to observe something. John Doe student says, oh, well, this is 3x minus, it's going to be 1. So 3x plus 1 times x minus 1, or x minus, no, 3x plus 2 times x minus 1, right? 2x squared, 2x minus 3, yeah. And then over x plus 1 times x minus 1. They say, oh, cool, the x minus 1 factor, and then I could just write this as 3x plus 2 over x plus 1. But remember, when you do that, when you cancel a factor, you technically need to write provided x minus 1 does not equal 0. And the reason for that, so you don't want to try and factor and cancel when it comes to finding domains because you're going to lose out on information. The issue being that yes, it's a factor of the numerator and the denominator, but you get 0 over 0. And what we know is that 0 over 0 is a indeterminate number. It does not like it, it's undefined. 0 over 0, we don't know what it is. So instead, what we do is we just set the denominator equal to 0. X squared minus 1 cannot equal 0, because if it did, we'd be dividing by 0, and that would cause an issue. So x cannot equal 1 or negative 1. If you want to, you can factor it by using difference of squares to verify that. But if you want to use the square root property, you can also do that. So those are the issues. Did I answer the question, though? Question isn't asking for where it's discontinuous. The question is asking where it's continuous. So those are the discontinuities. So if you look at a number line, if you don't need to draw a number line to figure this out, that's great. Kudos to you. You get one of those kudos bars from back in the 90s. Delicious. Does anyone remember kudos bars? Or is that before your guys' time? It was before we realized that we probably shouldn't give kids a bunch of sugar and call it a snack. But they were delicious. They had M&Ms. It was a granola bar with M&Ms in it. It's delicious. But here's -1. Here's 1. If you don't know how to draw it at first, that's fine. If you don't need to draw a number line to figure it out, awesome. But it can help you when you first start out. This needs to be plucked out and this needs to be plucked out. But everything else is fine. So it's continuous on negative infinity parenthesis to -1 end parenthesis, union -1 to 1, union 1 to positive infinity. And for part A, what I should have written is, or you could write continuous on negative infinity to positive infinity. CONT meaning continuous abbreviation, just because I don't want to write continuous. It takes way too long. Any questions on that? So use a number line if it helps. If you can do it, like the more you do this, the more you work with number lines and stuff, the better you get at it. But if this helps you at first, please do so.
So to get the 1 and the -1, you just simplify, and then you see what it can do.
Yeah. So you're looking for what it cannot equal, and it cannot be 0 on the denominator because then we'd be dividing by 0.
So
and we
you
can
just set it equal.
Yeah. So you can, like, I wrote x squared minus 1 can't equal 0. You can write x squared minus 1 equals 0 and solve it. It's not wrong to do that. Just make sure that you know that those are the points of discontinuity.
Right.
Yes. Isaac makes a great point. Next one. Love this problem because logarithms, you need it to be positive, right? You can only have the inside be positive in a logarithm. So what we're going to try and do is we're going to make x squared minus 2x minus 8 strictly greater than 0. Does anyone remember what these are? Nonlinear inequality. Best thing ever. Love solving nonlinear inequalities. They're an awesome thing to do. The reason why I bring this up now is that this is going to become useful to us in Unit 3. Being able to solve a nonlinear inequality going to be very, very essential. So if you don't remember, you set one side equal to 0, which we already have. Then you factor it. This is x plus 2 times x minus 4. It's greater than 0. That gives us the VIPs. That's what I call them. Technically, it's not a point, I know, but VIP has a much better ring to it than a VIV. A very important value, doesn't sound nearly as cool. But a VIP is x equals -2 and +4. Those are the things you're going to plot on your number line. So -2 and 4. However you want to solve a nonlinear inequality, that is your business. I don't care, as long as it's mathematically valid. I will show you the staple way, or like my staple way, which is the fastest way. There's one slightly faster way, but that requires understanding multiplicity. So if you learn the multiplicity trick, did anybody learn the multiplicity trick? Super nifty. Is that if you have an odd multiplicity, it changes sign. Even multiplicity, it stays the same. So both of these are multiplicity 1, so it'll change each time. But either way, I'm going to do it the normal way, which would be to plug in some test values. X equals -3, x equals 0, and x equals 5. Those are sufficient. Though if you do want to troll me, you can put in. If you really want to make it go off the page, you could do that. I'm waiting for a student to do that, to give me some lols, as the kids say. But anyways, if you plug in, all we're looking for is the sign. We don't care about what the number is. All we care about is whether the result will be positive or negative. So plugging in -3 into our factors, x plus 2 will be negative. And -3 minus 4, that'll be negative as well. A negative times a negative is a positive. We want our values to be greater than 0 strictly, meaning we want them to be positive. So this will be a piece that we want. Plugging in 0, 0 plus 2, that's positive. 0 minus 4, that's negative. A positive times a negative is a negative. That is a piece that we do not want. because we need our expression, we need our expression x squared minus 2x minus 8, we need that to be strictly positive. And last but not least, we plug in 5, we'll get a positive times a positive. That is a positive, and that is a piece that I want. So those are the two pieces. And because it's a strict inequality, it's strictly greater than 0, we have to exclude -2 and 4. So the answer is that it is continuous on parenthesis negative infinity to -2 and parenthesis union parenthesis 4 to positive infinity. Once again, you do not need to put the plus signs in front of your positive infinities. It's just what I do to make sure that I'm very definitive. So that if I ever have to take an exam again, I don't get marked down for that issue. It scarred me, yes.
So if the outsides were negative, the inside is positive.
Yes. So Esrom asks a great question. If this had been flipped, if instead, so don't write this down, but if this had been instead of this, if it had been negative, positive, negative, then this would be the only piece that you'd want, and your answer would be -2 to 4. It would only be continuous there. But luckily for us, not luckily, that would be ridiculous. It's not luck. It's just what it is. One thing as a reminder about this, we'll talk about this more and more later on. But one thing of important note is remember that it doesn't automatically just flip. So don't just assume that because your first one's positive that the next one's going to be negative. That's not guaranteed. Sometimes it is, but that's not something you should always test or use the multiplicity trick. So last one. This one's the tricky one. This one's for all the kit and caboodle. I don't even know if that's a terminology. Is that real? Is that a real terminology? No, it's not a thing. Okay, so that's not jiving. Surviving is more correct for the kids. So we've got two pieces. We've got a square root piece and we've got a rational piece. So the square root piece, we need the inside to be greater than or equal to 0. 2x plus 7 needs to be greater than or equal to 0, which, saving a little time, x needs to be greater than or equal to -7/2. Right? In order for the square root to be defined, we need the inside to be greater than or equal to -7/2. The rational portion also plays a role. X minus 5 cannot equal 0. So x cannot equal 5. So we have two conditions that need to be satisfied. I'm going to draw them in a number line to help us visualize it. But if you know the answer right off the bat, go right ahead and draw it. But looking at a number line, here's -7/2, and here's 5. From the red, from the square root, we know that we have to be greater than or equal to -7/2. But from the blue, from the rational expression, we can't have it equaling 5. So we actually end up having to exclude that. So our answer should be that this function is continuous on bracket -7/2 to 5 parenthesis union parenthesis 5 to positive infinity.
If it's not included.
Bracket means it's included. The way I like to think about it is imagine, like I didn't draw it great here. Let me redraw it to make sure it's better. If you draw a bracket, it's going through the line, so it is included. Whereas if you draw a parenthesis, it's not touching it. Yes.
So for the -7/2, why did we put greater than?
So excellent question. Square roots can be 0 on the inside, right? They have to be positive, but they can also be 0 because the square root of 0 is 0. So that's in stark contrast for the logarithms, which aren't defined at 0. Log base b of 0 does not exist, but the square root of 0, the 4th root of 0, the 16th root of 0, those are all, they exist. Excellent question. Now, I do want to mention something here just because it's an interesting concept. You don't need to write this one down, but I just want you to observe it. If the expression had instead been, if k of x had instead been the square root of 2x plus 7 plus 7 over x plus 5, right? Then the only difference is that plus, right? So we'd have, from here, we'd have x greater than or equal to negative 7 halves. And from here, we'd have x can't equal negative 5. But the answer will just be continuous on bracket negative 7 halves to positive infinity. That will be the answer. I want you to think about why. Why would it be that I don't write the negative 5? Think about it. We get to say one of the most annoying terms in mathematics ever, or like more specifically, one of the most pompous things that mathematicians will ever say. I've seen it several times in upper division textbooks, and it makes me want to punch the author through the textbook. This condition in orange is vacuously satisfied, meaning that it is automatically taken care of by the fact that we need to be greater than or equal to negative 7 halves, right? If you have to be greater than negative 7 halves, you're already greater than negative 5, because negative 7 halves is negative 3.5. So by virtue of this happening, this doesn't even matter. Does that make sense? Because it's not included. It's already, you're already past that point. So just as an interesting concept, this is a fun little tidbit. And that way because I love saying it, it makes me feel powerful. It's saying vacuously satisfied. Makes me seem better than other people. So that's why I like to say it, but just as an interesting observation. Okay. So we are not going to finish. We're going to start this one up. We're going to do this one. We'll probably finish this one, but we won't get to the other one. And then we'll continue from there. So what's up? It does. For this one specifically, the reason why it takes a whole page is because we're going to explain the process. I'm going to give you the step-by-step process to do this. So I need a little extra space to write down the process as well. So piecewise functions, notice that they weren't included in theorem 1.5.1 because piecewise functions are a whole myriad of functions that are just weird. We can create a lot of different piecewise functions, and trying to figure out their continuity requires a little bit of extra work. So step one is going to be find discontinuities on each piece within its domain or within its restriction. Do I have enough space? Let me just collapse some things. It's too much space. Within its apostrophe restriction. So find the discontinuities within each piece's restriction. What do I mean by that? Is remember that the function is only defined as the first one for values greater than or equal to 0. So the way I like to write this example, so in our example, we look at the two pieces. So for x greater than or equal to 0, f of x will equal 10 over x plus 1 times x minus 2. When our values are greater than or equal to 0, our function is equal to that. This function is discontinuous at x equals -1 and 2, right? but I'm going to exclude one of those values. One of those values is not necessary. Take a second to think about it. Don't answer it. Let everyone get a chance to think about it. But one of those values I'm going to cancel out. I'm going to cross out. Let me know the value. -1. Exactly right. S-term is exactly right. Because of the restriction. So I'm going to cancel this one out. I'm going to cross it out and say not in our restriction. So our function, that piece, yes, if I'm looking at this, wait, can't cover it up with my hand. If I ignore this, then yes, the function is discontinuous at x equals -1 and at x equals 2. But I'm not like getting rid of that. That is a requirement. Our function only equals that for values greater than or equal to 0. So I get to say it again. The x equals -1 is vacuously satisfied. So we don't need that one because it's not in the domain. If you were to draw this function, I can show you just as an aside. Here is -1, here is 2. And then so your function looks like this. Nope. The full function should look something like that, I think. Yeah, like this. Like that. That's the full function. But for us, we're only defined as that function right here. Our function only exists for values greater than or equal to 0. So we don't have that discontinuity -1 because that's not even part of our function. Does that make sense? So be on the lookout for that. So that is one discontinuity. Then we also have to check out the other function. For x less than 0, f of x will equal x minus 5. That is a line. And lines are fine. Lines are polynomials, and polynomials are continuous everywhere. No discontinuities because polynomial. Yes, it's not a very, very exciting polynomial. Sorry, x minus 5, you're just not that interesting. You don't have any squares or cubes or whatever, but it's still a polynomial. It's a degree 1 polynomial. And so polynomials continuous everywhere. So of course it's going to be continuous for values less than 0. If you draw that line, it's just going to be a straight line. You're never going to lift your pen off the page. So no discontinuities on that one. So we only have one discontinuity on the pieces. That's step 1. Look at each piece, find its discontinuities. Step 2. This is to determine if discontinuous at dividing values. Need to check the left and right hand limits to ensure the full limit exists. Let you write that down. It's a lot of words, so I'll let you write that down, and then we'll say it. So we need to determine if it's discontinuous at dividing values. Dividing values, not dividing value, because there could be multiple. I guess I should, if I really, really want to be particular, I should say values with an apostrophe, with the parentheses around the S. Because this problem only has one dividing value, but the next one has 2. Once everyone's written that out, why? Why is that step 2? Remember when we were finding one-sided limits and we talked about piecewise functions? Sometimes your piecewise function might look like this, right? Your piecewise function could look like this, in which case there would be a discontinuity at the dividing value, but your function may well look like this, in which case it will be continuous because you can draw it with this point gets filled in by the right function. So when you trace it, it's continuous there at the dividing value. So when it's a dividing value, you can't just plug in the full limit. You need to check the left and the right. And if they equal each other, they exist, and we're good. So in the example, we only have one value at x equals 0. That is our dividing value. We'll check the left-hand limit, we'll check the right-hand limit, see if they equal. So the limit as x approaches 0 from the right of f of x is equal to, what function would you be for values to the right? Take a second, think about it. This will be the limit as x approaches 0 from the right of which one, the top one or the bottom one? When our values are 0 from the right, we're talking about values slightly larger than 0, the top function. Because that we're equal to this function for values greater than or equal to 0. So this will be 10 over x plus 1 times x minus 2. And remember, try and plug in the value. If you get a number, that is the limit. And you will see that that is the actual answer because we're not going to be dividing by 0. So you can just plug it in. You can go through the motions and stuff, but if we look at it and notice that we're not dividing by an isolated x factor, so we can just plug it in. 10 divided by 0 plus 1 times 0 minus 2, that's going to be negative 5. The limit as x approaches 0 from the left of f of x, we're going to be the secondary function equals the limit as x approaches 0 from the left of x minus 5. Very, very nice function. So we can just plug in the 0 because we're not going to be dividing by 0 or taking square roots of negative numbers or anything like that. So this just becomes 0 minus 5, which is negative 5. They're equal. Sorry to keep you a little bit late. We'll finish off on next time, but I want to write down the last bit of this part, okay? So this means that the limit as x approaches 0 of f of x is equal to negative 5. Because the left and the right-hand limits agree. Remember, your full limit exists if and only if your left and your right-hand limit equal the same thing. John Doe student writes this. I marked John Doe student down by 1 point. Why? What is required for continuity? The limit exists. We just showed that. We need to make sure that the function exists. Because, be careful, if this had been x strictly greater than 0, then f wouldn't exist at 0, and it would be discontinuous. You see what I'm saying? We'll talk about that next time. We'll reiterate it. I'm going to keep it like that to remind us. But we'll finish off next time. If you guys have any questions, feel free to ask. Otherwise, happy studying on the weekend. Remember, your exam is next Wednesday. So happy studying. I'll post the solutions probably next week, probably on Monday. Okay. If you have any questions, feel free to email me. Otherwise, you guys have a great weekend. Have a good one.